Metal structures are generally joined by the process of arc welding, which utilizes electric energy to enable this joining. The most commonly used process is referred to as CO2 arc welding. Within the CO2 arc welding process, the base metal and welding wire are melted in an arc atmosphere that is covered by CO2 shielding gas. The shielding gas flows through the nozzle of the torch and protects the molten weld puddle. If this did not occur, the molten puddle would become contaminated and defect-prone due to the reaction it has with the atmosphere, which contains oxygen and nitrogen. The welding process is started by pulling a torch switch and adjusting the welding torch so that the wire is within a short distance of the welding start point. CO2 arc welding is considered to be a relatively simple and economical process. The components for the CO2 arc welding process are the welding power supply to feed electric energy to melt the welding wire, an automatic wire feeder, gas flow regulator for the CO2 gas cylinder, a remote control, and a welding torch handled by an operator. Inverter-controlled welding power sources are typically used because they offer better arc stability. Recently, full digital welding power supplies that include full digital wire feed systems are becoming popular. The welding wire is fed continuously from the wire feeder to the welding torch. There are two types of welding wire for the CO2 weld process. One is a copper-clad solid wire, and the other is a flux cord wire. Each wire is used for specific welding applications. A recent trend for solid wire type is for the surface to be treated without copper cladding. The shield gas flow is adjusted to 15 to 25 liters per minute by the gas regulator. This flow rate should be without moisture per the JIS specification. Welding amperage and arc voltage is set by the remote control. The welding results are influenced largely by the handling of the welding torch. For example, maintaining a constant tip to work distance influences the quality of the weld results. The purpose of the contact tip at the end of the torch is to feed the electric energy from the power supply to the welding wire by contacting the wire to the inside surface of the torch tip. Then arc is generated between the end of the wire and the base metal. This creates the molten puddle which joins them together. The welding results are also governed by adjusting welding current, arc voltage, and travel speed as an addition to the handling of the torch by the operator. Now let's explain the influence of these welding parameters. First, let's start with welding current. Welding current is adjusted by a dial on the remote control. The amperage setting is increased by turning the dial clockwise. This also increases the rotation speed of the wire feed motor, thus increasing the wire feed rate. In other words, the welding amperage is proportional to the wire feed speed itself in CO2 arc welding. This is a chart showing the relationship between welding amperage and wire feed speed. When the amperage increases, the thermal energy becomes larger and wire melting rate is increased. Compare the weld bead appearance when the welding amperage is changed between 200 amps, 260 amps, and 340 amps. As the amperage is increased, the amount of melted base metal is also increased due to the high melting rate of the welding wire, which results in high thermal energy. The weld pool size is changed when the amperage is increased, even when the travel speed is kept the same. The weld bead width becomes wider as the amperage is increased. This is a macro section of the weld bead. Weld penetration shape in the base metal can be described as pan bottom. The weld bead width and penetration is increased by increasing the amperage setting. Since the welding amperage is a major factor of the amount of penetration, welding amperage is adjusted based on the thickness of the plate to be welded. Next, let's check the effect of adjusting the arc voltage setting on the weld bead. Changes in arc length intensity are observed when adjusting the arc voltage. Differences in the arc phenomenon are observed when the voltage is adjusted between 16 volts, 23 volts, and 36 volts. This was done while keeping the welding amperage and travel speed constant. The arc length is proportional to the arc voltage. Lowering the arc voltage makes the arc length shorter and vice versa. These are macro sections of welded test plates showing the effect of changing the arc voltage while keeping the amperage constant at 200 amps. The arc length becomes shorter at lower arc voltages and the shape of the weld bead is convex. On the other hand, higher arc voltage causes a longer arc length and the shape of the weld bead becomes rather flat. The weld using an arc voltage of 23 volts is desirable, noted by the good bead appearance. Incorrect arc voltage will cause an unstable arc condition. This is an example showing the effects of low arc voltage. Due to the short arc length, the arc becomes unstable and generates a lot of spatter. In the case of a higher arc voltage, the arc is wide and creates large spatter balls. When the appropriate arc voltage relative to the welding amperage is selected, the arc is stable, creating a uniform sound. The setting of the arc voltage is important because it affects the arc stability and the bead appearance. The correct arc voltage selection relative to the welding amperage selection makes the arc stable and decreases the spatter. Next, we will explain the effect of the travel speed on the weld bead. The travel speed is defined as the torch movement along the welding line. Efficiency can be increased by faster travel speed, but generally the standard travel speed is about 50 centimeters per minute. This is an arc condition created at 300 amps, 30 volts, and a travel speed of 20 centimeters per minute. When the travel speed is too low, the weld pool is widened and the molten weld metal flows around and ahead of the arc to hamper the stability of the weld. This is noted by the unstable sound of the arc. If the travel speed is too fast, the arc moves ahead of the weld pool and defects such as lack of fusion or undercut might occur. Here we have the 3 samples of a weld macro section. These show weld penetration increases at lower travel speeds and decreases at higher travel speeds. The travel speed can be used as a good parameter to control the heat input and wire deposition rate into the base metal. Next, we will explain the effect of torch handling and how it changes the shape of the welding bead. The welding torch can be angled 5 to 20 degrees in the travel direction when welding. When the torch is angled in the travel direction as shown, it is called the forehand or push welding method. Contrary, when the torch is angled opposite to the direction of the travel, it is called the sweep back or drag welding method. Generally speaking, forehand welding method is more common since it is easy to observe the weld joint, bead appearance, and shield gas effectiveness. In the forehand welding method, the molten weld metal is pushed ahead of the center of the generated arc. This results in shallow penetration, wider bead width, and flat weld reinforcement because the wire is being deposited into the molten weld metal, which makes it difficult to penetrate the base metal directly. In the sweep-back welding method, the molten weld metal is pushed into the center of the generated arc. This results in deeper penetration, narrower bead width, and convex weld reinforcement because the wire is being deposited onto the base metal directly. The sweep-back welding method is used for special cases such as deep beveled welding that is able to handle this type of bead shape. Opposite characteristics are shown in the weld macro section when forward welding method and sweep-back welding method are compared. Observe the differences in penetration, bead width, and weld reinforcement. When the large welding amperage is induced onto a small wire diameter, as in the case of CO2 arc welding, the arc force is generated in the direction the wire is being fed. This phenomenon is referred to as the arc stiffness. The arc force is stronger when the current density is higher. Furthermore, the torch angle affects the penetration and bead profile. Hence, it is very important to keep the torch angle constant when welding. One more important item to note when handling the welding torch is try to keep the torch tip height constant. In semi-automatic welding, moving the torch in and out should be avoided, although the above problem does not happen in automatic or robot welding processes. When the torch is moved in and out, the electrical stick-out is changed. The welding amperage is decreased when the stick-out is increased due to increased electrical resistance. On the contrary, the welding amperage is increased when the stick-out is shortened. In this way, moving the torch in and out causes undesirable welding results due to the changes in amperage, arc instability, and wire deposition rate. One of the most important things to remember when handling the torch is to keep the torch tip height constant while welding. The welding operator monitors the distance between the nozzle and base metal to keep the wire stick-out length constant. The distance is typically 10 to 15 millimeters for lower amperages and 15 to 25 millimeters for amperages over 200. Finally, we will explain the influence of the weld metal transfer mode into the weld bead. In CO2 arc welding, the arc transfer mode transitions from short circuit transfer to globular transfer after around 200 amps. This is an image of the short circuit transfer mode using a high-speed camera. The bluish-white light at the end of the wire is the arc. This light repeats on and off. This is because at the moment the end of wire touches the base metal, the arc extinguishes and a large current flows between the wire and the base metal. The end of the wire is then melted off by the arc energy. This melted metal particle then drops into the weld pool via gravity. Hence, the short circuit transfer mode repeats on and off, and the number of times it repeats is usually between 40 and 200 times per second. In short circuit transfer mode, frequent transfers makes the arc stable and minimizes spatter. The weld pool is cooled down instantly when the melted metal particle drops into the weld pool because arc energy is not being added to the base metal. As described above, heat input to the base metal is relatively low, and so the penetration becomes shallow, which is desirable for thin plate welding. Next, we will explain globular transfer mode. In the globular transfer mode, a melted metal particle is formed at the end of the wire. The melted metal particle is then transferred to the base metal when the size of the metal particle at the end of the wire grows large and falls off due to its own weight, and this process generates spatter. In this mode of transfer, the wire generally does not short to the base metal, therefore the number of short circuits are less when comparing with that of short circuit transfer mode. Globular is in the range of 10 to 50 times per second. Therefore, the arc sound is loud and the arc is less stable. Large spatter balls can occur. However, higher arc energy is obtained. In the globule transfer mode, the penetration into the base metal is deeper, which makes it applicable to medium and thick plate welding. Let us summarize. The welding parameters are controlled by the welding amperage, arc voltage, and travel speed. The welding amperage mainly affects the penetration, the arc voltage affects the bead shape, while travel speed is related to the amount of weld being deposited. In addition, the control of the torch is critical to the bead appearance. Sophisticated operator skill and experience is required to achieve satisfactory weld results. Even with robotic welding operations, basic welding knowledge and control of the torch should be understood to be successful. The mag welding process is an acronym for metal active gas. Mag welding is defined by JIS as using an active shielding gas in the welding process. Therefore, when welding with 100% CO2 shielding gas or when welding with a mixture of argon CO2 shielding gas, both are considered mag welding processes. But the arc characteristics of these two welding processes are different. We will explain these welding processes separately, respectively named CO2 welding process and the mag welding process. For the mag process, it commonly uses an 80% argon, 20% CO2 gas mixture, and we will explain the mag process under this condition. The welding machine for the mag welding process is basically the same as the welding machine used for the CO2 welding process. As for the basic parameters of the mag welding process, the welding amperage, arc voltage, travel speed, and the torch control affect the weld bead in the same way as the CO2 welding process. We will explain the mag welding process mainly by arc phenomenon. In the mag welding process, melted metal particle transfer is divided into three types: short circuit, globular, and spray transfer. First, we will observe short circuit transfer. This example shows a 1.2 mm thick plate using the mag welding process. The welding parameters are 120 amps, 17 volts, and a travel speed of 70 centimeters per minute, with a 1.2 mm diameter welding wire. The transition from short circuit to arc is smoothly carried out, and so high-quality welding results are obtained with a stable arc and little spatter. This is an example of CO2 welding with the same material thickness. The arc is not as stable when compared to mag welding, and the amount of spatter is also increased.